Hello, I'm Andrzej Avdonin. I'm from the Institute of Physics, Polish Academy of Sciences. Today I'm presenting my work titled Characteristic Length of Conductivity of the Miller-Abrahams resistor network in 3D as function of the cell size. This work investigates the properties of Hoping electron transport and specifically the Hoping conductivity. This slide shows the difference between the Hoping electron transport and the more common free electron transport in semiconductors. Usually in semiconductors, the conductivity is controlled by point defects, as shown here. These defects contain loosely bound electrons which can detach and propagate in the crystal as a free particle. This process is shown in this process number 1 in the crystal lattice diagram on the left and on the energy diagram on the right. Simultaneously, a bound electron can also propagate through the crystal by quantum tunneling to a nearby empty state. This process is shown as process number 3, also on the left and on the right diagram. In general, Hoping is defined as tunneling between the localized sites in the crystal assisted by phonons. The equations that control Hoping conductivity are nonlinear. However, in the DC mode, if the electric field is small, these equations can be linearized, and then the system of Hoping electrons can be viewed as an equivalent circuit of resistors, which is shown here on the left side. This circuit is called the Miller-Abrahams resistor network, and in this circuit every two sides are connected by a resistor. Because of how this circuit was constructed, the resistors must be of a specific form, which is shown by this formula, and most important that the resistances depend exponentially on the distances between the sides and also on the localization radius of electrons, which shows how much the wave functions of the neighboring sites overlap. One of the goals of the theory is to calculate the macroscopic conductivity of an infinite resistor network. The solution was provided by percolation theory, and the reasoning goes like this. Let us first unplug all the resistors from the network and let us sort them, and let us then plug them back one by one, starting from the smallest one. First, the resistors will connect small groups of sites and will create small clusters. However, the resistance of the cell will be infinite. If we keep plugging the resistors back, there will be a moment when the last added resistor will connect two large clusters which are touching the opposite sides of the cell, and the current for the first time will percolate through the cell. This resistor is called the critical resistor. If the distribution of the resistances is wide enough, we can say that this last added resistance is much larger than all other resistances of the cluster. Then the entire voltage of the cell will drop on this resistor, and also the entire current will flow to this resistor. In this situation, we can say that the resistance of the entire cell is equal to the resistance of this critical resistor. If we keep adding all the remaining resistors back into the network, they will form paths which are in parallel with the critical resistor. However, because the distribution of the resistances is high enough, the currents is high enough, the resistances of these paths will be much larger than the resistance of the critical resistor, and very little current will flow through them. Thus, we can say that even in the fully populated network, the resistance of the cell is still equal to the resistance of this critical resistor. Because the resistances depend exponentially on the distances between the sides, thus we can say that the resistance of the entire cell depends only on one geometric parameter, which is this distance of the critical, or the separation of the critical pair. The scale-independent microscopic property is conductivity, and in 3 dimensions the conductivity is given by this formula. It depends not only on the cell resistance but also on the cell size. This function is shown here by the dashed line, and we see that when the cell size increases, the conductivity goes to 0. From the experiment, we know, however, that for very large cells, the conductivity stays finite. To solve this problem, the percolation approach assumes that very large cells are controlled not by a single critical resistor, but by a network of critical resistors shown here schematically. This network is called critical subnetwork. Each branch of this network of size LC contains a single critical resistor. Now, if we start from a very large cell and then decrease the cell size, At first the conductivity will still stay finite, but then when we reach cell sizes comparable to LC, then there will be a crossover from the regime when the network is controlled, but the cell is controlled by the network, critical subnetwork, to the regime when the cell is controlled by a single critical resistor. This point of crossover I call the crossover length. Then in the conductivity formula, this parameter should be not the cell size, but a characteristic length. In small cells, the characteristic length is equal to the cell size, but when we reach cell sizes equal to LC, the characteristic length saturates and remains constant and equal to crossover length. The purpose of this work was to calculate numerically the dependence of the crossover length on the site separation and localization radius. For that, two kind of simulations were made. In the first simulation, each cell was solved for potentials and currents, and then the conductivity of the cell was calculated. And in the second simulation, the percolation problem was solved for each cell, and then the critical resistance was calculated. Then from this formula, the crossover length, the characteristic length was calculated, and then from this plot, the crossover length was calculated. This is the result. The left plot shows the dependence of characteristic length versus the cell size for the ratio d0 over a equal 12. As an example, each dot here shows a simulation of an individual random cell, and indeed it follows the prediction, and the characteristic length was calculated from this plot as the average value of all values from the gray region. The result, the dependence of characteristic length on the ratio d0 over a is shown on the right plot. Here each point was calculated from a corresponding plot on the left side. This plot has a value in itself because it can be used to choose the right cell size when simulating coupling conductivity. It can also be used to test the prediction of percolation theory, which is shown here. The prediction fits the simulation in the range of arguments larger than 7. I got the exponent value of 0.83, and using the known value of critical distance, I got the unknown parameter a of 0.64. Then we can say that in general we have agreement between the prediction of percolation theory and the simulation. However, there are three caveats. First of all, we see that the points at small cell sizes predominantly fall lower than the prediction. The second caveat is that I had expected no noise at all in this region, but there is considerable noise for no known reason. And the third one is that I was expecting to be larger than 1, and it's actually smaller than 1. Another unexpected observation was found after a simulation of the average conductivity as a function of the cell size shown here on the left side. In this plot, each dot is a geometric average of 300 simulations, and I remind you that I was expecting the decrease of conductivity, some crossover, and then saturation of conductivity at cell size larger than the crossover length. However, in simulation the behavior is opposite. We see no saturation even in larger cells, and also if we take the point of maximum curvature as the crossover point, it does not correlate with the crossover lengths calculated previously, which are shown here by the dashed lines. After simulation of critical distance as function of the cell size, which is shown here on the right side, I found that the increase of conductivity with the cell size is mainly due to the decrease of the critical distance rather than the characteristic length of the cell. A second attempt was made to calculate the crossover length by using the average values of conductivity and average values of critical distance. This attempt has failed. The best approximation is shown here by the solid line for two values of d0 over a. One is equal to 8 and one is equal to 16. It is important probably to note that the error increases with smaller values of d0 over a. Finally, there is an unexpected universal behavior at large cell sizes. In this range, the normalized conductivity does not depend on d over a. This means that there has to be an additional factor f of L in the formula for conductivity. I propose that this factor comes from the poorly conducting dead layer on the cell surface. In the presence of such layer, the factor f of L has to have this form where T is the thickness of the layer. This dependence is shown on the left side by this black dotted line. All unexpected observations in this work are attributed to the mean field component of conductivity. Whereas the percolation theory is focused around critical resistors, the mean field component is the cumulative effect of all other resistors of the cell. For example, the total number of resistors increases as the cell size to the 6th power. And in the case of d over a equal 10, when the crossover length is 6.8, there is about 49,000 resistors in the cell. Thus, even though each of them carries very little current, there are very many of them in the cell. In the last slide, I summarize all the evidence of the mean field component. First of all, it can explain reduced values of the characteristic length and the increased noise at small cell sizes. It can also explain the presence of the dead layer and the universal behavior in this range. It can explain why the unknown parameter A was found to be less than 1, whereas A greater than 1 was expected. It can explain a lack of the crossover feature, which would be correlated with the LC calculated in this work. And finally, it can explain the inability to describe the average conductivity using percolation formula. Indeed, it is expected that at larger values of d over a, the percolation component would increase and the mean field component would become smaller. This is the end of my presentation. Thank you very much for listening.